So we're going to talk now about polynomials. This is an introductory lesson. So the thing that we're looking for here is the big picture. We're going to talk about the characteristics of polynomials. The next lesson will focus on a bit more of the nitty-gritty, the inside parts. But we're going to start with a sort of an overall picture, an overview of polynomials. So we're going to talk about polynomials as smooth curves, which is something we see from polynomials. Then we're going to look at transformations of a few monomials. We have learned about monomials already at this point, so you should, if you're not in my class, I guess, go find out about monomials. Then we're going to talk about the leading term test. That's a way we do end behavior. We're going to look briefly at zeros and turning points. We don't actually learn to find turning points without a calculator until calculus. We will learn how to find zeros without a calculator in pre-calculus, but not in this lesson. That's part of the nitty-gritty that we're going to learn next time, but I'm going to talk about them briefly as part of this lesson. So moving right into it, by smooth curve, when we look at the graph of a polynomial, we shouldn't see any corners. A sharp and sudden change in direction, that's called a corner, and polynomials don't have them. They also don't have any type of discontinuity, so you won't see a jump discontinuity or removable discontinuity, nor will you see vertical asymptotes. Those are types of discontinuities, and polynomial functions simply don't have them. Polynomial functions always have domain all real numbers. And the range will vary depending on the type of polynomial, so we'll get into that with specific examples as we move through the course. As far as what a polynomial looks like, I have a few examples. A polynomial is actually the sum of a number of monomials. So you'll notice each piece here has a coefficient and a variable raised to a particular power. The powers for polynomials are always whole numbers. So you're not allowed to have negative exponents and you're not allowed to have rational exponents. So there won't be any fractions or negatives in the powers. So 3x to the fourth power, that's a monomial. And here we have negative x cubed, that's another monomial. We're stringing them all up and adding them together. So polynomial is really a sum of a bunch of monomial pieces. And as such, because the monomials have domain all real numbers, and we're just adding them all together, we expect the polynomial to also work for all values of x. So polynomials are smooth curves, domain all real numbers. I'm going to now graph some transformations. The first one I have for you is x minus 3 all raised to the fifth power. So the basic formula or format we use for our transformations, we express as a times f of x minus h plus k. And in case you have forgotten, the number subtracted from the x is a horizontal translation. If we're subtracting a number, we're expecting a movement to the right. That's always backwards. So minus 3, because it's supposed to be minus, this 3 is positive, represents a move to the right. If this said x plus 3, that's x minus negative 3, would be a movement to the left. Any number added on the outside is a translation up if it's positive. If you see a negative on the outside, that's down. And then the number multiplied in front is going to produce a vertical dilation. That's a stretch. Well, it's a stretch if a is big, and it's a shrink if a is small. Either way, it's referred to as a dilation. So that's basically the categories we're thinking in when we do a transformation of a monomial. In this case, a is missing, it's 1, so there is no vertical stretch factor. K is also missing, it's 0, so we're not moving up or down any. We normally expect a monomial function with a positive coefficient to start with its vertex at 0, 0. In this case, that minus 3 gives me a translation 3 spaces to the right, so the vertex has been moved to 3, 0. Normally, x to the fifth power, that's an odd power, so we expect x to the fifth to look like this. It's going to go in opposite directions. 5 is a pretty high number, 3 is more common. I probably didn't draw this flat enough in the middle. It should be flatter in the middle and steeper on the sides than you'd expect from, say, a cubic function or a linear function. But they all go through, the basic function goes through 1, 1, which has also been shifted 3 spaces to the right. So that's 4, 1 there. And it's also going to go through 2, negative 1, because there's no vertical stretch, there's no dilation. So flatter in the middle, steeper on the sides. Looks something like this. So there's my basic sketch for x minus 3 to the 5th power. My second example is x to the 6th minus 1. In this case, I notice that the negative 1 is not inside the power. There's no parentheses there. So the negative 1 is actually k. It's a vertical translation. So this is down 1, which puts our vertex at 0, negative 1. Because this is a 6-degree monomial here, it's going to go up on both sides, a positive coefficient as well. So I'm expecting it to go through these points. It's going to be even flatter and steeper on the sides, although from 5 to 6, it might not be a noticeable difference if you look at the picture. So very steep sides and sort of flat on the bottom. And there's x to the 6th minus 1. For my third example, I will pull out all the stops. Negative 2 times x minus 4 to the 3rd power minus 3. Here I have all 3 represented. I have a vertical dilation, I have a horizontal translation, and a vertical translation. Since the inside is backwards, that's going to translate to 4. The outside's not. 4 negative 3 puts me right here. That's my vertex. Normally, I would expect the next point to be 1 higher and to the right 1. But because of the vertical dilation, because A is negative, it's actually upside down. This one's going to go down on the right instead of up on the right. It's been reflected. And it's going to be twice as tall, so I need to go down 2 spaces, not 1. And it will be symmetric rotationally around this point. Because 3 is odd, it's going to go in opposite directions. So down on the left, or sorry, down on the right, up on the left. Notice it's not nearly as flat in the middle, partly because this is 3 and not 5, but also because I multiply by 2, it's going to stretch out the middle part here. So that's transformations of monomials. I also want to talk about the leading term test. You'll note my overall picture, like where this is heading off the screen, has a lot to do with the power and whether it's even or odd. When we look at a polynomial, it's got a lot more pieces in it than just the one being transformed. But the good news is that as x gets big, the terms with the higher power tend to dominate the expression. By the time you get to even 10, 10 to the 4th power is 10,000, whereas 10 cubed is 1,000 and 10 squared is 100. So the number in front is like an order of magnitude bigger than all the rest. By the time we get to, say, x is 100, that effect is doubly so. So when you're looking at a polynomial and trying to figure out its end behavior, that is, you're not concerned with what's happening in the middle, you're only looking to see where it ends up, you can ignore all of the terms except the highest power of x. We call that the leading term, and that's why this is called the leading term test. We ignore all the rest. This has a positive coefficient, which means I'm expecting it to eventually go up on the right. I don't care how much it wiggles in the middle, that's not what I'm looking at. Because the power is even, I'm expecting it to go the same direction on the left that it went on the right. So I expect this function to go up on both sides. If I'm writing that as a limit, I would write the limit as x approaches positive or negative infinity of d of x is positive infinity. Since they're the same, I can put them into one limit because they're both headed toward positive infinity. As far as e, this one is not written in standard form, and that'll mess you up if you're not paying attention. The front term, what looks like the leading term, is actually only squared, whereas the second term here is to the 5th power. So in order to write this in standard form and see the true leading term, I need to rearrange this into descending powers of x. which means the leading term is actually 2x to the fifth. This is a fifth degree polynomial. So the coefficient is still positive, which means I'm expecting to go up on the right, but because the leading term has degree 5, it's odd and will go opposite on the left side. In this case, then, the limit as x approaches positive infinity of e of x is positive infinity, but the limit as x approaches negative infinity is actually negative infinity, not positive infinity. For my last example here, the leading term is right in front there. The leading coefficient is negative, which means it's going to be upside down. It's going to go down on the right. It's fifth degree, which is odd, so other way, or up on the left. So this is the opposite of the one we just did. The limit as x approaches positive infinity is going to be negative infinity, and the limit as x approaches negative infinity will be positive infinity. That's the leading term test, which leaves me with only one thing left to talk about, zeros and turning points. Actually finding zeros, as I said, is not something we're going to do right now, but I am going to talk about how many. With a fourth degree polynomial, or I should say as polynomials increase in degree, they can turn and wiggle a lot more. Turning point on a polynomial is where it's been going in one direction, and it's going to make a change and switch from increasing to decreasing or from decreasing to increasing. So this graph here has 2 turning points. You'll also note it has 3 zeros. Now the rule is the degree of a polynomial has to be at least as big as the number of zeros, or that is a cubic function can have at most 3 zeros, the same. The number of turns that you can see in a polynomial graph is 1 less than that. So a third degree function can only have 2 turns, and you'll note that's what we have here. So for a fourth degree function, whatever else is going on can have at most 4 zeros, and at most 3 turns. This one here is fifth degree, which means it can have at most 5 zeros and at most 4 turning points. They can have less. Sometimes the function will have fewer turns, and we'll get into why that happens and what to do about that when we dig in. Right now we're just worried about what's the most number that we can have, or if we know how many turns there are, what's the smallest degree. That wraps it up. If you will recall, we started with smooth curves and what makes it a smooth curve. We did some transformations on some monomials, which led us into our leading term test. Finally, how many zeros and turning points can we expect? In the next video, then, we'll dig into the zeros and figure out how to use them.